Good morning, everybody, and welcome to the CEIA Maths Tutorials online again this Saturday. And this week we have the probability tutorial, and it's going to be delivered by Collins, who you've already met. With that, I think I'm going to let Ed take the floor and deliver the probability tutorial. Okay, so over to you, Ed.
Thank you, Eamon. Good morning, everyone, and welcome to this maths tutorial on probability. As Eamon mentioned, I've met some of you before on previous tutorials. I gave a tutorial on indices and logs and also on trigonometry. So I'm very pleased to be giving you this tutorial today on probability. Now, I'll have to be honest and say that this topic wouldn't be probably the favorite one for engineers anyway. And some of my colleagues and friends who are engineers, their eyes roll a bit when we talk about probability. But it is a very important topic, and as you see, it has some wide applications. And when I was preparing for this tutorial, I started off looking at the principles of permutations, combinations, and so on, which are a lead into probability. And I think if you take your time with it, spend time understanding the principles, the fundamentals, then it becomes quite an interesting topic, and the questions should be readily solvable during the Leaving Cert. Now, most of the probability questions don't require a lot of working. I have one example later on from a Leaving Cert paper, last year's Leaving Cert paper, and that requires a little bit of work. But in the main, they wouldn't require the level of working that trigonometry question or calculus question or whatever. So it does, however, it does require a lot of knowledge of the topic, and it's important to understand the tools and techniques that are used to solve the problems, to be comfortable with them. And once you're comfortable with those tools and techniques, then the actual working of the problem won't take too much time. So you can gain a bit of time when you're doing the questions during the Leaving Cert, if you have the fundamentals and techniques right. So that's where I've come from in preparing this tutorial, to make sure at the end of it that you will be more comfortable using the techniques, using the tools that are required for solving probability questions. So hopefully you'll get some tips and help from this tutorial. Now, what are the applications of probability? Well, they vary from, as you see there on the left-hand corner, actuarial activities in relation to insurance. So insurance companies use probability quite a bit. What are the chances of somebody having an accident? What are the chances of a fire in a building, and so on? So it is used extensively there. It's to do with risk, the level of risk and the premium related to risk, and so on. So used a lot there. You see an image there on the top right-hand side of the International Space Station. We looked at the International Space Station before in one of the other tutorials, but in this case, the image is showing a study that was done to assess the potential damage from impact from particles in space. So there's a lot of debris now in space. Space satellites are breaking up other items and so on. So it's possible that the International Space Station would be hit by a small particle, not of very large mass, but traveling at very, very high speeds, which could do a lot of damage. Then there would be consequential damage depending on where the space station was hit. You potentially could take the power out of the system. So probability was used for this study. There's no real detail here on the actual numbers, but the colours do represent different levels of probability of impact. So it is used quite a bit in engineering, and I've seen it used in relation to risk, the probability of an incident occurring on a pharmaceutical plant. It's important to assess risk and then to take mitigation actions in relation to that risk. So I have seen it used out in industry, quite an important application there in relation to health and safety. And then finally, the last image is related to quantum mechanics, and probability is used in that field of study. Relatively new field, the 100 years old, obviously. Albert Einstein and others, Schrödinger and other very good scientists worked in this area, developed the concepts, and probability comes in quite a bit there. So if any of you go on to study physics in college, and particularly quantum physics, then you will be looking at this area as well, and the applications of probability. So hopefully that gives you some background to the applications of probability, a very useful tool in engineering and science. So what's going to be the scope of our tutorial this morning? Well, we're going to start off with the first fundamental principle of counting, the multiplication principle. And then we're going to look at the second fundamental principle of counting, which is the addition principle. We're going to then move on to permutations and, very importantly, combinations. Combinations are used extensively in problem solving for a lot of the problems that you'll see on the Leaving Cert involving probability. So you have to be very confident in working with combinations. We'll have a quick look at Pascal's triangle and binomial coefficients. We'll probably take a break then at that stage, possibly around 11 o'clock or 10 past 11 for 10 minutes or so. And then we'll move on to probability proper. And we'll be looking at some of the concepts of probability, set theory, which is very important in solving problems, the axioms of probability, and the probability of success and failure, the rules of probability, general addition rule, and then the general multiplication rule. And we'll finish off with a Leaving Cert question. So hopefully you'll find all these topics very interesting. Just to prepare for some of the work we're going to do, we are going to do a number of questions. So if you could have a notepad and calculator as well, because I'm going to show you some of the functions on the calculator that will be used for solving probability questions. So if you could have a pen and paper and calculator ready, we'll give you a bit of time to work on some of the problems, and then I'll go through them with you. I think it helps have a bit of interaction in the tutorial doing this, so hopefully you'll benefit from those exercises as well. Now I want to give credit to Aidan Rountree's Effective Maths textbook 2, which you see the photo of there. So I used this textbook when I was preparing the slides. I had studied probability briefly in college and in other areas, so I had to go back and study it again in a bit more detail to prepare for this tutorial. So I've used Aidan's, in the main, Aidan Rountree's textbook, which I find very good. I've included a a reference to that at the end of the tutorial as well. So the first fundamental principle of counting, multiplication principle. So this comes up quite a bit. You're going to be using this in problem solving. So let's say we have a hypothetical restaurant which only serves starter, mains and desserts, and there's limited options for each. So for the starter, you see there's option 1 and 2. There's only 2 starters, quite limited menu here. So there's only super salad. So in terms of the outcome, the number of options, there's 2 here. However, there's a bit more. There's one more option in terms of the mains. There's a meat, fish, and vegetarian option. So there's three outcomes there from a selection. And they're quite good in desserts in this restaurant. So they're giving us four options here. We can have ice cream, we can have fruit, we can have meringue or tiramisu. Now, if a customer coming in has to order a meal which must include 1 starter, and it's very important this now in the multiplication principle, and 1 mains and 1 dessert, then the total possible meal outcomes are going to be 2 for the starter, multiplied by 3 for the mains, multiplied by 4 for the dessert, and that equals 24. Very important, the and means that you multiply the options. And you'll see this coming up again and again as we go through the tutorial. So that's the first fundamental principle of counting, but one that you're going to be using a bit, as I mentioned. So here's an example of a code that will be developed using the multiplication principle. So a security code has to be comprised of 2 uppercase letters. That's very important now because uppercase and lowercase and so on have a bearing in relation to the number of options. So we're just talking about uppercase letters in this case in the code, and 2 digits, which must be between 0 and 1. So 0 is allowed. How many code combinations are possible? So for the first character in the code, it's any uppercase letter. 26 letters in the alphabet, they're uppercase. Obviously, if we had lowercase, so then we'd be talking about 52 here, but we're only talking about uppercase here. Again, the second character in the code is an uppercase letter, 26 options. Character 3 in the code is a digit from 0 to 9. So we've 10 options because we're including 0 there. And the same for character 4. So using the multiplication principle then, the total number of combinations is 26 letters multiplied by 26 because it has this and here, multiplied by 10 because we've another and here, multiplied by 10 again. And you see in the case of this relatively simple code, it ends up being 67,600 different combinations of code. So you can see how numbers grow very quickly when you're using the multiplication principle. So that's the first principle covered. The second fundamental principle of counting is the addition principle. So again, we have our same menu here. So everything is the same. Two possible starters, 3 possible mains, and 4 possible desserts. However, the rules around what the restaurant offers are different here. So if the restaurant offers the following meal options, so we can have a 3-course meal comprised of 1 starter, 1 mains, and 1 dessert, or this is very important, the or here, a 2-course meal comprised of 1 starter and 1 mains, or a 2-course meal comprised of 1 mains and 1 dessert. But then what are the total possible meal outcomes or meal options here? So you see we're using the multiplication principle here for the first option here. So the 3-course meal, so that's 2 by 3 by 4. And we use it as well here for the second option. It's 2 by 3, because we can have 2 starters and 3 mains, so 2 by 3. And then finally for the last option, a 2-course meal comprised of 1 mains and 1 dessert. So there's 3 options here. 3 by 4 is 12. But you'll notice here that, okay, we multiply each of these, 24, we get 6 and 12, but we add them here. So when you see an or here, you will need to add, and that's why it's called the addition principle. So our options here are 24 plus 6 plus 12, which is 42. 42 options here. So just be careful, but there is really, we're showing the addition principle here, we are using the multiplication principle in here inside the brackets. So again, that's going to come up. Some problems will just involve the multiplication principles, some will involve the addition principles, or some will involve both. So you definitely need to be happy with using these and to know when to apply them. But often the questions, the key is if you see or, and so on. So, and I could have put in the text here, 3-course meal comprised of 1 starter and 1 mains and 1 dessert. Then that would lead you into, first of all, use the multiplication principle here, and then move on to use the additional principle. Now, we'll have a quick look at sequences, permutations, and combinations. So this number theory, all these combinations, permutations, and so on, this part of mathematics is used a lot in coding, in security, ciphers, and so on. So increasingly now, with the use of the internet, security is a key thing, and encryption of data and so on. So this topic is going to become, it is already a very important topic in mathematics, but will increasingly become important as people share more and more sensitive data, financial data, and so on. I don't know if any of you have seen the the film Enigma, which was about the machine used by the Germans during the Second World War, and how a team was set up in the UK, in Bletchley Park, to crack that code. All that work actually led on to development of computers. So it's a very interesting field. But I'm going to go through here sequences, permutations, and combinations. But really, it's combinations for problem solving that I've seen most of the problems I've looked at on the Leaving Cert papers. But it's important to understand the differences between, certainly between permutations and combinations. So we will look at sequences briefly as well. So in the table here, I've summarized the differences between sequences, permutations, and combinations. So in the case of a sequence, order is important and repetitions are allowed. By repetitions, so if you have the number, the digits 1, 2, 3, and you want to see the different sequences that can be made up from 1, 2, 3, in a sequence, you can use 1 several times in that when you're looking at the different options. But in permutations, you're not allowed to use that number 1 again. It can be used once, but not twice in a series. So that's an important difference between a sequence and a permutation. So repetition's not allowed, but order is important in a permutation. So what do we mean by order? So you'll see it here, a permutation does not allow repetitions. So 3, 2, 1 is a permutation of 1, 2, 3, but 3, 3, 1 is not. But an order is, in the case of 1, 2, 3 is one order, 3, 2, 1 is another order. So order, that's what we mean by order here, the order in which the digits appear. Then in the case of a combination, order is not important, and again, repetitions are not allowed. So a combination is a selection of elements. So in a selection of elements, in a combination, an apple and an orange is the same as an orange and an apple. In an arrangement, 1, 2, 3 is not the same as 3, 2, 1. So some of these topics can be a bit tricky, but hopefully this table will help you. And in the end of the day, when you're doing problems, as I say, most of it is going to be around combinations. So just to remember that in a combination, order is not important and repetitions are not allowed. I have some examples showing the difference between sequences, permutations, and combinations, which will help reinforce these concepts. So a permutation is an arrangement of objects in a particular order with no repetitions. So if we take some digits here starting with 1, so we see with 1 we can just have one permutation, it's just 1. I've written this in terms of a factorial, so it's 1 by 1, and that equates to factorial 1, which is 1. If we've 2 unique digits, 1 and 2, well then the permutation is 1, 2 and 2, 1. So that's two possibilities there. 2 by 1, factorial 2. Likewise, for 3 unique digits, we can have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1, which is six possibilities, 6 options here. And that is factorial 3, 3 by 2 by 1. So this is the symbol for 3 exclamation mark is the factorial. If we carried on with n unique digits, well then the number of permutations of n unique digits is factorial n. So this is summarized down here, that factorial n equals n by n minus 1 and so on, where n is a natural number. And very importantly, factorial 0 equals 1. There is a proof for this that you can look at online if you're interested, but it can be a bit confusing. You'll be inclined to think, oh, factorial 0 is 0. It's not, it's 1. So that's very important to remember for this and for other topics. So the terminology here, going to using n if we have n different objects and they're taken or at a time. Sometimes you see n used for number of objects and then k for the number selected. So that does come up in some tutorials or some videos, textbooks, and so on. But I'm going to use the n and the or here throughout the tutorial. So the designation is NPR for permutation, and here's the formula for it. So it's factorial n divided by factorial n minus r. So it can also be written in this form, n by n minus 1 and so on, all up to n minus r plus 1, where n again is a natural number and factorial 0 is 1. And very importantly, r must be less than or equal to n. So obviously r can't be greater than n. That doesn't make sense. So if you have 6 objects and you're asked to select 7, that doesn't make sense at all. But this formula will work for r being equal to n. And I've just developed it there. So if r equals n, then you get this situation, npn. So it's factorial n divided by factorial n minus n, which is factorial n divided by factorial 0. And as we know, factorial 0 is 1, which equals n. So that's what we've seen in the previous slide. So here's an example of working out NPR. So how many 2-letter permutations can be made from the letters A, B, C, D, and E? So the first thing is to see, well, what's our total set here of letters? So we have 5, so n equals 5. We're asked to select 2 of those, so r equals 2. Therefore, we're looking for 5p2, which is factorial 5 divided by factorial 5 minus 3. And I've just worked it out there, is 120 over 6, that equals 20. So this option is available on your calculator. We'll be looking at that now in a minute, but it is important to understand how it's developed and be confident in using the tool. Now we're coming on to the very important combination. So remember, order is not important in a combination. So this slide goes through the combinations of n different objects taken r at a time. So we're dealing with the same n and r here, and I've again brought the designation here as NCR. Now you will see in your textbooks, in solutions and so on, you'll see brackets with n, the number n at the top, and or at the bottom. We look at that now in a minute in solving an example. But just for the moment, I just want to get you familiar with the NCR designation. This formula is somewhat similar to NPR, except this is factorial n divided by factorial r multiplied by factorial n minus r. So there's an additional factorial r in the denominator there. And you see it's worked out there. And again, the rule applies here where n must be a natural number. Factorial 0 is 1, and again r is less than or equal to n. And again, if we put in r equal to n, then we get factorial n divided by factorial n multiplied by factorial n minus n, which is equal to factorial n divided by factorial n, which equals 1 in this case. So that makes sense. If you're taking all the objects, what are the combinations? So if you have 6 objects and you take 6, well then there's only one possible combination where order is not important. So here's another example again. We're going to use the same 5 letters and we're going to have to pick 2 of them. So how many 2-letter combinations can be made from the letters A, B, C, D, and E? So again, we plug in n equals 5, or equals 2. So we have the 5C2 situation here. So it's factorial 5 divided by factorial 2 multiplied by factorial 5 minus 2, and worked it out there. So that's 120 over 12, which equals 10, which is less than the permutations example. So that's important, that you're going to have less combinations for the same situation than you would have for permutations. Now we'll have a quick look at Pascal's triangle. Pascal was a great French mathematician and philosopher, and did a lot of work around probability, and he developed this triangle. So I've just shown 8 rows. So starting with row 0 here to row 7, and it goes on. It can go on obviously to infinity, but it's very interesting. There's a lot of symmetry here. So you see ones are on the last element, the left-hand side and the right-hand side of each row. And then as you go down through the rows here, you see that if you were to add 1 and 3 here, you get 4. 3 and 3, you get 6. 3 and 1, you get 4, and so on. So there is a symmetry here. And if you look at it here, you've 1, 2, 3, 4, 5, 6 along here. You've 1, 2, 3, 4, 5, 6 along here, and so on. And then there's a series here developing along these lines here. So very, very nice, in some ways artistic representation of numbers. But anyway, getting back to the binomial coefficients, what are the binomial coefficients taken from the triangle? Well, it's an NCR situation here. Again, now this is where I mentioned the designation that NCR can be written here as N over R inside brackets. In the case of binomial coefficients, N is the row number. Now remember, we start with row 0, and R is the element number. And again, the element number starts with element number 0, 1, 2, 3, and so on here. So let's look at the case of row 5, element 2. So here we have row 5 and element 2. So if we key in N and R in here, 5 and element 2, which R equals 3, then we get 10 here. So which corresponds to the number in Pascal's triangle. Likewise, in the case of row 7, if we key in 7 and the element 3, then we end up with 35 here. So just important to understand where binomial coefficients come in. They may turn up in some other problems that you'll be solving, some questions. So that's the source of it, but it does come back importantly to NCR. Now, here's a summary of the elements of a sequence, permutation and combination for n equals 1, 2, 3 and or equals 2. So in the first case, if we take a sequence here, so these are all the possible outcomes or options for a sequence for taking two of the digits out of 1, 2, and 3. So we can have 1, 1, we can have 1, 2, we can have 1, 3. We can have 2, 1. We can have 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. So if you add them up, we have 9 different options here, and that equates to n to the power of r, or in this case 3 to the power of 2. So that'll stand. We've seen that in previous slides in terms of the number of options in a sequence. However, if we move along to the permutation, the NPR, and we put and here is 3 and r is 2. So we duplicates are not allowed here. So 1, 1 isn't allowed. We've already used 1, so we can't use it again. 1, 2 is obviously allowed. 1, 3, 2, 1, 2, 3, 3, 1, and 3, 2. So order is important here. So 1, 3 in a permutation is not the same as 3, 1. So that's why they're shown as 2 different options here. So again, if we were to add these up, we get 6, or total them 6 different options there. And then finally, the NCR, the combination. So we put in n equals 3 or equals 2. Again, 1, 1 won't be allowed. 1, 2 is allowed. 1, 3 is allowed. We don't include 2, 1 because we've already included 1, 2. So remember, the orders is not important here. So 1, 2 in the case of a combination is the same as 2, 1. So 1, 3 is an option, and 2, 3 is an option here as well. So the total here is 3. So you can see the trend appearing here. There are a lot more elements here in a sequence than there are 3 more elements in sequence than there are in a permutation. And again, there's 3 more in a permutation than it is in a combination. So that's a trend there. So if you do happen to get a question that would include a permutation, calculate a permutation, and also calculate a combination, and the combination doesn't turn out to be less than the permutation, then something is wrong. The combination will always be less than the permutation. The permutation will always be less than the sequence. So I hope this slide gives you a good idea of the difference between the two. But really,
sorry to interrupt you there. I've got a question in from a student, and
yes,
it says, I don't understand why 1, 1 cannot be used and 1, 2 can be.
That's,
I suppose that's for the
permutation.
NPR, yeah.
Yeah, for the permutation, that once you've used the digit here in, it can't be used again just for this selection. It can be used, obviously, it can be used again down here in a 2, 1, but that's the rules of permutation. It's a sequence, yes, it can be used in, but in terms of the rule of that, that's the rule of a permutation. You use the 1 here, 1, 2, but you cannot then use the 1 again. There are some additional resources online. I'll be referring to them. There's a very good website, the French website, but translated into English, which has permutation and combination generators. So you can go in there and investigate a bit more around permutations and combinations, and also sequences. But really, the rules are that when you're generating a permutation, you cannot, within this element here, if you used one, you can't use it a second time. Okay, so as I say, really it's combinations that are going to be the key tool that we will be using, but it is important to know the difference between the two.
That's great. Thanks, Ed.
Thank you, Him. Now, thankfully, we don't have to calculate these MPRs and NCRs from scratch. We can use our calculator. This is my calculator. Taking a photo just to show you the options on the calculator that are used to calculate NPR and NCR. And just as an aside, there is a list of approved calculations for the Leaving Cert on the Leaving Cert exams website. I've included a reference to that website at the end of the tutorial. So just make sure that your calculator is an approved calculator. Some calculators are a lot better than others. So some may not have this function, but it'd be important for doing probability questions that you would have a calculator that provides this function, because it's going to make it a lot easier when you're doing the questions, as you'll see. So quite easy to use. So if we were calculating an NCR here, we key in N first, we hit Shift, press the NCR button here and key in the R, and then we press equal to. So it's very easy to calculate NCR with this type of Casio calculator. But please check out your calculators, make sure they're approved, make sure that that you have good functionality in them, and then make sure that you're happy calculating NPR and in particular NCR with the calculator. Now, this is where I'm going to take a little breather for a couple of minutes and get you to do some work. And Eamon is going to bring up some poll questions just when I've gone through this question, and then I'll work out the solution just on the screen here using the pointer. So this is taken from last year's Leaving Cert examination. So it's paper 2, question 1, part B. So an examination paper is made up of 2 sections. Section A consists of 7 questions, and section B consists of 8 questions. So the paper contains the following instruction. From section A, you must answer 1 question, and note this and now, and any 3 other questions. So that's from section A. Now, obviously, and you must also, from section B, you must also answer any 4 questions. So find how many different combinations of questions may be answered if a candidate follows this instruction. So I think there's a couple of things here to note here. We're talking about and. We're given 7 questions here in part A, 8 questions in part B. So there's ands here, and we're talking about combinations here. So how many different combinations of questions can be answered? So maybe, Eamon, could you bring up the poll questions, please? Thank you. So I'm going to give you a few minutes to think about this question, and then come up with the answers to the poll questions here. So what principle of counting should be used to solve this question? Should we use the addition principle or the multiplication principle? And then we've seen there that we're talking about combinations. So we're going to be doing NCR calculations here. So how many NCR calculations are required to be completed to solve this question? 1, 2, or 3? So maybe you'd have a think about that, and maybe also if you could have your calculators ready as well, so that you can actually work out the NCR calculations for this question when we do them on the screen. So I'll give you a couple of minutes there. It's going to be the multiplication principle again, because we saw earlier on it's the and here. You know, we have to select a number of questions from part A and from part B and so on. So that was the key in that it's the multiplication principle. In fact, yes, there are three NCR calculations that we're going to have to do to solve this question. So now the writing with the pointer isn't going to be pretty, but it just saves going out onto another application. So the first NCR calculation we're going to do is this. So N is 1 and R is 1. So why is that? Well, from section A, you must answer one question. So it's 1 of 1. A little bit tricky, I thought, putting that one in, but that's the way it is. So it's 1 of 1. You must answer question 1. So you've no option there. You know, it's what we saw earlier on. The combination is just 1 there, so it's 1 of 1. So that's the first. So we're talking about the multiplication principle. So we're going to multiply here. And now this is the tricky bit. This is where there's very little writing to be done, but there's a lot more thinking than some other problems here. So in section A, there's 7 questions. We must answer question 1, and then any other 3 questions from the remaining questions. They haven't written that in, but it's from the remaining questions. So our N has gone down from 7, or you know, you might think it might be 7, but it's gone to 6 now because we've already answered question 1. So the 3 questions we're going to answer in section A, the remaining three questions are going to be from an option from 6 possible questions. So that's where you really have to be careful here. So in this case, N is 6 and R is 3. And again, multiplication because of the and this is probably the easiest part now of all, because we're into section B, and from section B you must answer any 4 questions. So there's a total of 8 questions on section B, and we must answer 4 of them. So that's it, really. That's it. So it's a matter of getting out the calculators. We've seen that NCR, where if N and R are equal, then that's 1. So we shouldn't need the calculator for that. For NCR with N6 and R3, that's going to equal 20. And then finally, for N equal to 8 and R equal to 4, that's going to equal 70. So our total number of combinations is 1,400. Use the so in the end, it came out quite easily, but it required a bit of thinking. And certainly, from what I saw from the poll there, some of you would have taken the opportunity of 3 NCR calculations, but some may have taken the option of 2 NCR calculations, which would have been incorrect. So hopefully that gives you an idea of the application of the multiplication principle and combinations and so on to solve a problem, a fairly recent one, and hopefully it'll increase your understanding of those tools and techniques. Now, I think Eamon, we might take a break before we move on to probability. I know we're a little bit ahead of the time, but it is just coming up to 11 o'clock. So it's kind of a natural break here before we move in to the core of the tutorial on probability, if that's okay.
Absolutely, that's fine, Ed. Is it a 10 minutes you want to be back for 11 or 11?
10 past, I suppose. Yeah, we're just
10 past 11.
Yeah.
Okay.
Okay.
We'll see you all back here at 10 past 11. So for part 2 of the probability tutorial. Okay, so bye for now. Welcome back, everybody, and hopefully you've had a little break there. And we're going to have the second part of the probability tutorial by Edmund Collins starting now. Okay, over to you, Ed.
So welcome back, everyone. Hope you found the first part of the tutorial interesting and helpful. And now we'll move along to probability. So this little diagram I thought was a good introduction to probability and the mathematical aspects of probability. So you'll see there probability ranges from 0 to 1. 0 is included and 1 at either end of the scale. But then in the middle there, you'll see what's called the even chance, or the 50-50. We often talk about that. There's a 50-50 chance of this. So that's a half. And in probability, and as you see, as we go through the questions, we often show them as fractions. So 11 over 260, 1 over 2, or whatever. So that's important to remember. So probability can't be greater than 1 and can't be less than 0. So if you do a question and you end up with a negative number for probability, something's gone terribly wrong. Likewise, it's always good to check your answer if it is a fraction to make sure that it's less than 1. Because again, if the answer is greater than 1, something's gone wrong. So you need to go back and check your calculations. So there is a range, obviously, in between 0 and 1. There are an awful lot of potential outcomes there. Just looking at a die there showing the 1 in 6 chance. So if you toss a die, it's a number between 1 and 6 will come up. So there's a chance of so the chance of, let's say, getting 1 is 1 in 6. The chance of getting 4 is 1 in 6 in that case. And it often in probability in textbooks and so on, they talk about tossing a coin. So a balanced coin and uneven, or a coin that hasn't been tampered with, of course. If you toss that coin an infinite number of times, the chance of getting heads is 1 over 2. The chance of getting tails is 1 over 2, but it must be an infinite number of times. So it's a bit like a series you move towards the chance of the 50-50 chance. So probability concepts. So the first thing is that normally they talk about a trial in probability. So you're conducting an experiment or trial, and that has outcomes. As you saw on previous slides, we did talk about outcomes. The sample space, very important here in probability. The sample space designation S is the set of all possible outcomes. So normally when you're tackling a probability question, the first thing you'll do is calculate the sample space. So that's a set of all possible outcomes. So the next concept is this event. It's something that may or may not occur when an experiment is conducted and is a subset of the sample space. So in the case of tossing a coin, that the event is that it's going to be heads or tails. So that's the event in that case, but it may or may not occur when an experiment is conducted. So then in order to calculate out the probability of an event, that's shown as P in brackets there, that's the number of time the event occurs over the total number of trials. And then underneath that, we're showing that probability must be greater than greater or equal to 0 and less than or equal to 1. So that's really just showing what we saw on the number, or the probability line, that the probability must be between 0 and 1, 0 and 1 inclusive. So the probability of equally likely outcomes, PE, is R over N, or in this case, it's the number of favorable outcomes over the total number of possible outcomes. So E over S, that's how you calculate probability. So the calculations in probability are relatively straightforward. It's just a matter of getting the data correctly, and certainly sample space is the first place to start. So we're going to use now techniques we looked at in the first part of the tutorial to solve this problem. So combinations, multiplication principle, addition principle, other things. We're going to use that for this problem. So this is from Aidan Rowntrie's book. So it's a good example to start us off on the journey of probability. So a bag contains 4 red, 3 blue, and 5 white markers. So 3 markers are to be drawn at random from those in the bag. Brian bets that all 3 markers will be of different colors, while Katie bets that all 3 markers will be of the same color. Determine who has the greatest probability of winning. You're correct, you have addition and multiplication principles are used, but it's the number of possible outcomes is 220. So how do we arrive at that? Well, the first step in solving the problem was to use the NCR to calculate the sample space, so the number of combinations. So the N, you see we had 4 of one color, 3 of another, and 5 of another. So the N in this case is 12. And we're going to select 3 from that. So the NCR in this case is 12 over 3 there, as you see. So the total possible combinations. In this case, is 220. So we had to work on the combinations first, which is the sample space. No, it may be a little difficult to make the bridge across that, and I see some of you may have struggled with that, but that's a key one there. We have to look at all the different combinations. So sample space is 220. So our first event there. So for event 1, all 3 markers will be of different colors. So we need to write this out to help solving the problem. So we say we're going to pick 1 from 4 red, because there's 4 red markers, and we'd pick 1 from 3 of the blue markers, and we'll pick 1 from 5 white markers. So again, we're going to calculate the NCRs for each of these different options. So it's 4-1 multiplied by 3-1 multiplied by 5-1. So 4 by 3 by 5. And that gives us a total of 60. The number of possible events there is 60 using the multiplication principle. So it's quite easy then to calculate the probability of that event is hash E over hash S. So that's 60 over 220. Normally we simplify this if we can. So we bring it down to 3 over 11. And again, just checking, it's less than 1. It's not negative, so it looks good from that point of view. So 3 over 11 for the first event. So if we write down what the second event is, for event 2, all 3 markers will be of the same color. So in this case, we're saying we would take the options here would be 3 out of the red, out of the 4 red, or 3 from 3 out of the blue, or 3 from 5 white. So you notice the or and the or, which indicates we're in AND territory here. So that's why we're using both multiplication and the addition principle here in solving this question. So again, we calculate the NCRs for each of these. So 4-3 plus 3-3 plus 5-3, which is 4 plus 1 plus 10 equals 15 using the addition principle. So again, for this event, we calculate the PE, which is 15 over 220. So it's 3 over 44. Again, we do the check, not negative, less than 1. And it's interesting as well. We can bring something else in here. From intuition, from our knowledge, we would say yes, that looks right, because it's definitely more likely that if you put your hand in the bag, you're going to pick 3 different markers, then you're going to pick all of the 3 of the same color. So intuitively, that looks right. So again, you use common sense, your experience in the real world when you get a solution. If your calculation had said that the probability of the second event was more likely than the first, well then again you should go back and check, because in the real world that wouldn't be the case. So in summary, therefore, the event 1 has a greater probability of occurring. So again, there's quite a bit in there, but when you break it down, I think it's important to break it down into the steps when you're trying to solve a problem. It helps to improve your understanding of the subject and the techniques. Now, set theory, we have to do a little bit of set theory, which is used in probability problem solving. And one of the questions we'll be looking at later uses set theory. So it's important that you're happy with the concepts and the principles here. So normally what's shown here is that we have the sample space is the box, if you like, rectangle here, and that's why S is shown outside of that. So that indicates the total sample space. And then within that, there's the event E, the circle here. So the event E is always a subset of the sample space. So here we have this designation. You should be all familiar with this from set theory, but it's A intersection B. So it's this shaded part here, means an event where both A and B occur. So that's that point there. And then again, this designation A union B, U, B means that either A or B or both will occur. So it's all shaded there. So you can have A or B or both occurs. Now, this is an interesting situation here. There's no intersection. So the intersection here is 0. A intersection B equals 0. Therefore, A and B are mutually exclusive. They're called are disjoint. So this is often used in questions too. So watch out for that, disjoint. So there's no intersection. There is a reference, again, at the end of the slide pack here to some videos and so on around set theory. So if you're a little unsure, it might be worthwhile looking at those, building up the confidence in set theory. But it is relatively straightforward when you see it there, but those videos may help you with understanding. Now, axioms of probability. Well, our friend here is again, probability event must be greater than or equal to 0, less than or equal to 1. So that's one you should be quite familiar with by now. First axiom. The second axiom, the probability of the sample space is 1. So the sample space is everything. So the probability of getting that is you're sure you'll have everything. So that's one part of that axiom. And then the probability of the null set is 0. So that's either end of the probability line. Then the third axiom, the probability of A and B equals the probability of A plus the probability of B if A and B are disjoint sets. So you saw that where there's no intersection. So that's an important axiom. The probability of A and B equals the probability of A plus the probability of B. And that can be expanded out. If you have A, B, and C in their disjoint sets, then that axiom holds true for that situation where you've three disjoint sets. So the probability of A and RB and RC equals probability of A plus probability B plus probability of C, and so on. So they're relatively straightforward. Again, it just helps in your overall understanding. You need to bring a number of things together when you're solving problems, but the set theory helps with the understanding of probability. Now, this is a very important concept, and it can be used quite a bit in problem solving and probability. So it's to do with the probability of success and failure at the complement of an event, as we often talk. So it's designated by E dash here. So E dash is the complement of E. So what is the complement of E? That's the elements of E, of S, sorry, that do not belong to E. So if we take our rectangle here has been the sample space. The event here is inside the circle. It's everything else. The complement of E is everything else. So there's a couple of good principles here now that the complement of E and E are disjoint sets. There's no intersection. That's interesting. So therefore, the sample space is E or the complement of E dashed. That can be written. So I should have put in another set of brackets there. Probability sample space is the probability of E union E dashed. And then because they're disjoint sets, from our axiom, we can say then we know that the probability of the sample space is 1. And we know that if there's disjoint sets, the probability of E union E will be the probability of E plus the probability of E dashed from our previous axiom there. And we can turn it around and say, therefore, the probability of E equals 1 minus the probability of the complement of E. Therefore, just writing it out in this way, the probability of success equals 1 minus the probability of failure. Now, this can be very useful in problem solving because sometimes it's easier to calculate the probability of failure than it is of success. If you calculated out the probability of failure, then you take it away from 1 and you're left with the probability of success. And you'll see again, this comes up in one of the problems later on. We use this technique. So we use P equals 1 minus P E dashed at the complement of E. So very important concept that will be used. So this is an example of using this success and failure again from effective maths 2. So a multinational company with operations in France, Italy, and Ireland has a board of directors which consists of 7 French, 6 Italian, and 5 Irish directors. A group of 3 directors is to be chosen at random to attend a conference. What is the probability that at least 1 Irish director in the group is selected? And I underlined at least. So it's important to note here that if the term at least is included in the question, then it's potentially a prompt to consider using a success and failure approach. In this case, success is getting 1 or 2 or 3 Irish directors in the group. So there's quite a bit of work involved in that. However, failure is the probability of getting no Irish directors in the group, which is easier to determine. So it'll only be by practice and looking at different questions that you'll come to decide in any particular case what's the best one to use. But certainly in this case, there's a lot of work in calculating the probability of success. So better to go with the failure option. So I'll just give you just a few minutes to think about that question. Maybe think about how you would approach it. We haven't got a poll on it, but again, just to spend a little bit of time thinking about the sample space, the different options. Again, we're going to be using NCR. What sort of NCR calculations are we going to do? What formulae, probability formulae are we going to use? Sometimes in problem solving, takes a while to work it out. You may not get it all in one go, but if you're 75% or 80% there for this question, then the next one, you'll get better and so on. But at least with problem solving, you just start somewhere. It's like doing crosswords or whatever. You just start into it. Start writing down what you know. So what do we know here? What are the NCRs, the numbers? Write them down. So we're talking about three. So three directors here. So that indicates, yeah, we're going to be choosing 3. So I'll just give you a few minutes there to spend a bit of time writing some facts and data down to help with the problem solving, and then we look at the solution. Okay, so here's the work solution here. Step 1. Step 1 is to calculate the total number of possible outcomes, S, using NCR. So N is calculated by adding total number of directors, 7 plus 6 plus 5, so 18. The R here, we're selecting 3, so the NCR 18 over 3, that equals 816. So that's total number, and the total number of outcomes in the sample space is 816. So we're going to take the failure approach here. So we're going to, in step 2 here, calculate the outcomes of getting no Irish directors using NCR with the 3 directors chosen from the 7 French and 6 Italian directors. So that's important there. So now we've shrunk the sample space down. So we're going to ignore the Irish directors, the 5 Irish directors, and we're just going to deal with this sample space now of the 7 and 6. So N is 7 and 6, which is 13. But again, we're going to be picking 3. So R is the same at 3. So the NCR here is 13 over 3. And that works out at 286. So step 3 in this is to calculate the probability of the failure. So remember now, we're saying is that the failure is no Irish directors. So our event here is 286, and our sample space is 816. So it's the probability of failure, this case, is 286 over 816, and we can simplify that down into 143 over 408. Again, it's less than 1, greater than 0. So, sorry, not negative. So we're okay here. So that's the failure. But the last step then is to calculate the probabilities of success, and we know from the definition in the previous slide, the probability of success is 1 minus the probability of failure. So we just calculated out there 1 minus 143 over 408, which equals 2 0.65 over 408. Again, the number is correct from a probability point of view. So a lot easier to do it this way, using the success failure approach than if we'd just gone for the success. So hopefully that helps with the understanding of the tools. A little tricky there, obviously, in the first step would have been straightforward enough, but it's probably the second step. That's a tricky one there, where, how do you calculate the outcomes of getting no Irish directors using NCR? But there are good examples around that you should try, and the more you do these, the more proficient you will become.
Sorry, Ed, I've got a couple of questions in from students.
Okay.
Which you may be able to answer.
Yes.
First one is, do you write your final answer as a fraction?
Yes.
Decimal in these questions, or
no.
Does it matter?
I don't think you'd lose any marks if you see any of the sample solutions, Eamon, in any of the textbooks. They're written as a fraction. Now, and they are simplified as well. So I think, in fairness, I think somebody marking a script, it would be quite unfair if they took marks off you for not bringing 286 over 816 down to 143 over 408. I mean, you've got the answer. It just hasn't been simplified. But any of the solutions I've seen, fractions are used. I haven't seen decimal. But I again, if you calculate it as a decimal, I don't think you would be penalized for that. But it's probably to do with the answer, the decimal, the number of decimal places, rounding, all that sort of thing. That's why they keep it as a fraction. You're not getting into this thing, well, is this to 3 decimal places? How many significant figures are, but it wouldn't be significant figures in this case, but it'd be decimal places. So yeah, keep it at a fraction. Another rule of probability now, called the general addition rule. And interesting enough, this comes up in the question we'll be doing towards the end of the tutorial. Now, again, there's some designations used here. So in this case, it's A / B means A, not B. And obviously we've come across this, so A intersection B, or A and B, and then in this case it's B, not A. So these are mutually exclusive events, disjoint events, so that's important. So again, we're used to this now, the rectangle S, A and B here, but the part that's A but that's not B, so that's not part of the intersection, if you like, is this section here. Then we have the A and B here, shaded in yellow, and then we have the B, not A, so excluding the intersection. So if we take the total, the probability of A or B are both equals x plus y plus a z. Now, if we rearrange this, we just add x and y together, close the brackets, and we add y and z together here and close the brackets, and then we add in another minus y here because it has to equal, this line has to equal x plus y plus z. So we have a minus y here. So in this case, the x plus y, we have this full circle here. That's the probability of A. And the the y plus z, full circle here, which is the probability of B. And then the y is the probability of A and B. So that is an important addition rule. So we're saying the probability of A or B or both equals the probability of A plus the probability of B minus the probability of A and B, because they're mutually exclusive. Because these events are mutually exclusive. However, if A and B are mutually exclusive, so if we move them apart and there's no intersection and they're disjoint sets, then we know that the probability of A and B is 0 because there's no intersection. Therefore, this simplifies the probability of A or B or both equals the probability of A plus the probability of B. So certainly worthwhile studying that a bit. It is straightforward, but it's again addition rule that's used in problem solving. So another tool in the probability toolbox. So again, we're coming across another designation here that we haven't seen before. It's B bar A. So this implies that the probability of B conditional on A happening. So that's just something you need to be familiar with that. If they give you a question with conditional probability, it's going to be more on the complex end of probability questions. You have to be comfortable with it, but hopefully you won't get into that level of complexity. But we have to be ready for it. So the probability of B conditional on A equals the probability of A and B over the probability of A. If each outcome is equally likely, then the probability of B conditional on A is the number of calculating out the outcomes for the probability of A and B over divided by A. It's important to note that if A and B are independent events, then the probability of B dependent on A equals just the probability of B because they're independent, and the probability of A dependent on B is the probability of A. So again, just writing down the conditional probability here, we can multiply across here by the probability of A. So we can switch the equation. So we end up here with the probability of A and B equals the probability of A multiplied by the probability of E dependent on A, which is the general multiplication rule. And that simplifies down into the probability of A and B equals the probability of A multiplied by the probability of B for independent events. So you'd see later on that we're going to use this general multiplication rule for independent events in problem solving. As I say, this conditional, we're moving up in the complexity stakes here when we're talking about conditional probability, but certainly this one is one that will be used. So you need to be happy with that rule there.
Sorry, Ed, I've got one question from a student, and it's
yes.
What does the bar mean? The straight bar.
It's conditional on A. So the probability of B is conditional on A happening. So that's what the bar means there. So that's where with the conditional probability. So that's what the bar is there. So not to be confused, there's intersect U's and intersections and all that sort of thing, and then there's backslashes and so on. So you need to be very careful with them, So, but if you see conditional probability coming up and you see the bar and so on, that'll be the indication there. But you need to be careful because there is the bar and there's the backslash, and that could cause a bit of confusion. Okay. So we're doing quite well on time here. So going to be going through this question here, which is from, again, 2019, paper 2, question 6, part A. So there's quite a bit of working out in this one, which is very typical of probability questions. But it's a good question because it's going to cover quite a bit what we've looked at in the last few slides. So I'll work through that on the pad here. So I just have to switch out. Now, can you see that, Eamon?
Yes, I can see it. Fine. Thanks, Ed.
Very good. Thank you. Okay, so this should look familiar from what we've looked at before. Just enlarge it there. So the first good news here is that we're talking about independent events. So two independent events, F and S, are represented in the Venn diagram shown below. Now P, F, and we should be familiar with the designation. F backslash S means F, not S. So what that means is that when we're talking about F not S, it's that part of the Venn diagram. So that equals a quarter, or 1/4. Again, you can see this back to the previous question. They're showing this has a factor. Then the next part of the Venn diagram, the probability of F and S is here. All right. So that's 1/5. And then the probability of S not F. So again, similar to what we looked at, F not S. This is part of the Venn diagram, and that's given to us as X. And then the complement here. So you can see it's very important that you're happy with the designations, the terminology here. So the saying here, the probability of F or S, sorry, the complement of that. So it's anything outside of F or S, anything outside of this part of the Venn diagram equals Y. So they're saying here that X and Y don't equal 0, and we're to find the value of X and the value of Y. So it always helps, even though they've given you that information in the question. I think when you're problem solving, it just helps you to settle into the problem by writing down what you know, what you're given, and just have that in the solution. So I like to do that rather than racing ahead of it. So we're given this. So the probability of F not S is 1/4. We're given this. The probability of F and S equals 1/5. And we want to find probability of S not F equals X. Now, the first thing to note is, well, we have the probability of F not S, but what is the probability of F? And the probability of F equals 1/4 and 1/5. So we're getting this total here. So we're bringing in the intersection part here. And that equals 9/20. Now, the first thing is to note here, they're independent events. So we've known from our previous rule for independent events, the probability of F and S for independent events is the probability of F multiplied by the probability of S. So we know that from up here, we know that the probability of F and S is 1/5, so we can substitute that into the equation. So the 1/5 probability of F and S is 1/5. And we've calculated out that the probability of F is 9/20. It's multiplied by the probability of S. That implies the probability of S equals 20 over 45. Just doing a bit of algebra. Okay. So, but we also know that the probability of S is equal to X plus a fifth. So that's good news now. The S equals X plus a fifth. And that equals to, so we've calculated out the probability of S, that equals 20 over 45. So it's a matter now of just calculating what X is. So X equals 20 over 45 minus 1 over 5 or 9. It's 9 over 45. So that's equals 11 over 45. So there's the first part of the question. But the key here was using this, that for independent events, that P, the probability of F and S equals the probability of F multiplied by the probability of S. So that was the key part of the question. The rest was relatively straightforward. So the next part of the question, is the complement. And again, we should be very familiar now with our success, failure, and so on. That the probability we'll be using the probability of success 1 minus the probability of failure. So so before we do that, we just need to calculate one more thing here. That's the probability of F union S, or F or S or both. And again, that's straightforward because there's a number of ways we can do it, but the way I've chosen to do it is just add up each part of the Venn diagram. So, it's a 4 plus a fifth plus 11 over 45. So this part, and this part will give us everything in the Venn diagram, which is F US. So that works out. Just need to be careful with your addition here, your algebra, but so it comes out at 625 over 900. So now we want to find y, and that equals the probability of the complement of F US, and that equals 1 minus the probability of F US. So that equals 1 minus 625, 625 over 900, and that equals 275 over 900, and simplifying we get 11 over 36. So it's a good example, I think, because it covers quite a bit what we did in the previous slides. Bit of working out a bit more than the usual probability question, but I hope it all makes sense, and certainly go back and study it again if you're unsure of some of the concepts there. But it brought a lot of things together, I thought. A fair question, but did bring quite a bit in terms of the understanding of F naught S and so on, the F and S, the probability of those, the probability of S, not F, and so on, bringing it all together, and particularly this rule here in terms of the probability of F and S equals the probability of F multiplied by S. That was a key one. The rest of it was just algebra working out, and of course this here, the probability of failure, the complement equals 1 minus the probability of the event itself. So that's that question. So I'll just switch back. So we've done quite well. We're at that. That's the last of the examples I have to show you this morning. I will just one last slide here, just to go through some of the resources that we've talked about during the tutorial. Obviously, Aidan Rowntree spoke there. Effective Maths is a good resource. There's 2 books, Effective Maths 1 and Effective Maths 2. Probability is covered in Effective Maths 2. If you're interested in learning more about techniques for mathematical problem solving, then I would strongly recommend you looking at this book, Solving Mathematical Problems by Terence Tao. This guy was a child prodigy in mathematics, won the Maths Olympiad, so on, and continues to work in maths. He gave a talk a few weeks ago remotely from the States. It was very good talk. He's very good, but his mathematical solving techniques are very good, and I have that book. I haven't been through all of it, but if you are interested in developing problem solving techniques, then that would be a good book to go to help you with that, because there are different techniques that can be used, but certainly practice. You need to get as many questions you can, practice them. They're not all going to work out. You're not going to get it at the first go when you start off, but the more you do, the better you'll get, the more understanding. You may have to refer back to your textbook, to this tutorial or others, whatever, if you're doing something on probability, but certainly the practice is the key in mathematics. Keep doing it, and you'll certainly get a lot better. Over the tutorials, we've talked about the Khan Academy. That's very good, not only for mathematics, but also for science subjects. If any of you are doing physics, chemistry, whatever, it's a great resource, and the tutorials are very good, very easy to understand, very well put together, very well presented, and there are some videos there on probability statistics and so on. So again, another source. I like to use different sources, not just the one textbook or the one video, whatever. And go to different sources, and you'll get different presentations, different views of the subject, and that increases your understanding, I found. So don't just stick to the one source, the one resource. Now, when we were talking about permutations and combinations, and the question, why are there no duplicates allowed, and so on, I would suggest going into that website there, www.decode.fr. Very good, because there's some very good interactive tools there where you can actually put in select letters, select numbers, and then the system will generate all the various permutations or combinations for you. You can see them listed, so you could say, 5 digits, whatever. Let me see every permutation or combination. But obviously, combinations, as I say, are the area you're going to be spending most time in. But if you want to develop your understanding more, the difference between permutations with duplicates or sequences, whatever, then I would suggest going into that website. Just found it by chance, but it is a good website. I mentioned then when we were going through Venn diagrams, certainly go into that short video. Very good video on Venn diagrams. Covers most, a bit more than what we looked at there, but again, another good resource. And finally, please go into the examinations.ie website. A great resource there. First of all, you're going to get all the past exam papers, so you should really be going into them. We looked at some examples there, but there'll be more. So for other topics, definitely recommend going into the past exam papers and start doing the questions from them. They also give the marking schemes. There may be a tendency to look at the question, then switch over to the marking scheme. Give it a try. If you're stuck, definitely go into the marking scheme. What's interesting in the marking schemes is that it gives alternative ways of solving the problems. And you'll see for some of the problems or questions we looked at today off the exam papers, it gives you a number of different options. My way, the way I did it, is one way, and there may be other ways of solving the problem. So it will show you that. It will give you an idea of how marks are allocated and so on. But really, to develop your skill, you should, when you're trying the questions, just give them a go, and then if you're really stuck, go over a look at the marking scheme and see, can you work out from that what the solution might be. So we're finished a little earlier. I thought it was going to take a bit longer, but I hope that you have got some useful information, tips and techniques on probability. Certainly, I found going through it that it wasn't as bad as I thought it was going to be. And once you become familiar with the key techniques, that you are able, you will be able to tackle the exam questions. So again, I wish you all the best with your studies in this difficult time, trying to get through all of this. But hopefully, please keep attending these tutorials, and maybe in the future I'll be presenting on some other topic. Thank you. All the best. Bye.
Thank you very much, Ed, for a great presentation and lots of examples and the probability for the Leaving Cert. And thank you also for Cathal in the background. I just want to recap a couple of things that Ed has said about the resources available. Okay, don't forget your log tables on page 33 and a few more pages after that too. You're probably already familiar with the examinations.ie that Ed was just talking about a few minutes ago. There's the website decode.fr where you can generate permutations and combinations. Your calculator, don't forget, practice using your calculator. Don't leave it until the last minute, and make sure when you're going into the exam that your batteries are okay in your calculator. Or if you get a new calculator, make sure that you practice using it before going into the exam, and also make sure and check that it's on the allowed calculators list, because you don't want to be in the exam hall and then being told that your calculator isn't allowed, and then maybe being given a calculator that you've never seen before. So just something to keep in mind. And as always, the Khan Academy has got a lot of resources for practicing maths. So with that, thank you again to Ed for a great presentation, and to Cathal also on the panel. And see you next week for the sequences and series tutorial. Okay, so bye for now.